Right, I'm going to speak to you then. I'm hopefully going to catch up some time because this needn't necessarily be sort of all in depth, but I think some of you will be interested in some of the research that has been going on in my little patch in connection with the University of Leeds. It's all about the Bombardier Beetle and its illustration of biomimetics, which is a growing subject in the universities, where people are getting inspiration, as I've indicated here, from looking at nature. And it's something which is not just true for this bit of work on the Bombardier Beetle, but it's also true for things like Velcro, which was discovered by someone realizing that some plants have hooks on, or with their seeds have hooks on, and that led to the invention of Velcro, which is commonplace today. Many other things like geckos' feet have been examined very carefully and right down at the micro scale, in fact, almost getting towards the molecular scale, where they have tiny little hairs which enable them to walk upside down, and they're making robots based on that. Many other inventions have actually really been due to copying nature. Indeed, the first powered aircraft was actually made by the Wright brothers by copying what was happening with the birds. That's really probably the most amazing example of biomimetics, where they got their inspiration by properly understanding what birds were doing. So there's more on that, as I indicated in this book, and it is an example of biomimetics, learning design from creation to inspire innovative engineering. There are implications to design. We need to be careful, though, about this God of the gaps idea, which those who believe that God used evolution in particular will accuse those of us who believe in creation of thinking. But the answer to that is it's not that which we do not know which is going on here. It's that which we do know which is pointing to design. So the suggestion of that argument, oh, you're just believing in a God who fills in the gaps of the stuff you don't know, is completely on the wrong foot. And you need to be ready for that argument when people try to push that against us, saying that to believe, they would say, in a simplistic view of creation, they would regard us as being, promoting just a very simple idea, that you're just believing in a literalism in the Bible, that you don't realize how complicated things are. Well, the point is that the engineers amongst us, and I include myself as both a mathematician and an engineer, seeing as a lot of this is engineering, actually shows to us that there is such sophistication in what we uncover, what we are discovering, whether it be about the eye, which we've just heard about, or whether it be about this Bombardier Beetle. It's actually all the things that we do understand, and we're not saying we understand everything, points to the design features which are to do with not just one item, but many items needing to be there together in order for the system to work. One of the biggest arguments for design is systems engineering. Andrew didn't mention this in his last talk, but really when he was talking about the eye, he had lots and lots of aspects to seeing where all the systems had to be working interlocked together. And it's the same with the Bombardier Beetle. There is an implication to design because of the systems that are involved, where you've got interdependent subsystems to make the overall system work. So in the Bible, you have this verse, Romans 1:20, which I've just mentioned, but also Colossians 1, which says that for by him were all things created that are in heaven, that are in earth, visible, invisible, whether there be thrones, dominions, principalities or powers. All things were created by him and for him, and he is before all things, and by him all things consist. Or the word there is to hang together. So it is an amazing point that God has not only made everything, but he sustains everything, and by him all things consist. And Hebrews 11 says, things which are seen were not made of things which do appear, which again is strongly emphasizing that Christ is the Word, he's the Logos, he's the principle behind everything that is made. So coming to the Bombardier Beetle, where is this found? How does it work? We're going to go through some of these aspects as we go through what I'm going to say this morning. So, first of all then, where is it found? And we'll look at some of these other things as well. Just let me... Sorry about that. I won't be doing all that, and not necessarily all the subtitles. But let me tell you where it's found. It's found in a number of places. It's found in Africa, found in Asia, it's found in North America, and even here it's been found. Some have been found, amazingly, in the south of England, where it's a little bit warmer. It's usually near water, and it has to be not far away from also places where there are rocks where it can hide. You don't find them very often here, but they are creatures which squirt out of their backside, and it's that we have copied. It's the spraying ability. They are close to water, and they will also, as I say, be usually hiding under some rocks. They prefer to be, as most beetles, hidden from other creatures. There are other creatures which will try to prey on them, and those creatures will be frogs, spiders, birds, or ants. But the Bombardier Beetle usually gets the better of each one of them. What does it do? Well, let me explain. It ejects a mixture of chemically heated steam, and these noxious chemicals come out of its back end. It's a separate system to its digestive tract, so it's not just, doing a noise like sometimes we might do. We won't go into detail. It's not doing that. And it wards off these predators that I've mentioned, ants, birds, spiders, and frogs. And the beetle has been known to lose, but it generally wins. And the amazing thing about this beetle is that it has a movable exhaust turret, which actually can even be brought forwards and be able to eject this noxious mixture in any direction it wishes. So I'm not going to be able to tell you today about the sensory mechanism. Nobody has quite grasped how that sensory mechanism, as far as I can understand, I don't think anybody has yet written on this, but there is a sensory mechanism such that it knows from which direction the attack is coming from. That, as far as I know, has not been understood and yet copied. But what I'm going to talk about is the spray system which it uses to defend itself. So this is what you might see if you find a Bombardier Beetle. This is in a laboratory, of course, and you might hear that sound as the Bombardier Beetle ejects the blast out of its backside. That was actually in Professor Tom Eisner's laboratory in Cornell University when I was working with him in New York State. And he was the one who really did all the initial work in the biology, and a wonderful scientist, and it was a privilege to work with him for a little bit and to get a lot of ideas from him. But he suffered from Parkinson's disease and has passed away now. But and it was great to know him just for a few years. Here's another film of the Bombardier Beetle from the BBC film The Alien Empire.
Few creatures will risk annoying a Bombardier Beetle. It mixes a cocktail of deadly chemicals in a special chamber. They react and explode at boiling point from its rear end in an awesome chemical weapon.
So that's been slowed down a little bit so you can actually see the cloud of stuff coming out. In fact, for a while we kept some Bombardier Beetles in our kitchen. Don't worry, we weren't eating them, but we could actually prod them and could see a cloud of gas actually come out from them. And you could even get a stain on your fingers from the quinone, which is in the stuff which is coming out. And I'll tell you more about the chemistry in a moment or two. But let me just show you another film which has slowed things down a bit more. This is Tom Eisner from Cornell actually discussing it. Here we go. Right.
One of the really amazing things about this animal is its ability to spray in a very beautifully aimed fashion. And that shows up very nicely when you put the animal on indicator paper. And what I'm going to do now is I'm going to pinch very lightly one leg after the other, just as if I were an ant biting these legs. I'm going to start with the right hind leg, right front leg, left front leg,
this is where it's slowed down a bit more.
At 400 frames per second, the action has been slowed down, but not enough to see the individual pulses. So they went to a lab and filmed the beetle at an even faster speed, at an incredible 4,000 frames a second. There were the pulses, each one corresponding to the individual bursts of sound.
Quite amazing, as you see the slowed down version right down to such that you could actually see each of the individual blasts about 500 times a second, so you're having about 10 frames per blast there, which was really quite extraordinary in those days. It was quite some time ago that was, as you could see, filmed with a cine camera. But a lot of information was gained from that there was individual explosions, which then helped Tom to make the proposal that it was those individual explosions which gave you the notes. So you actually hear a note, you hear a E, right, of that particular frequency on the piano. Imagine 256 hertz, middle C. When it's a bit further up than that, it's actually twice that, so it'd be 512 or thereabouts, so the C above. So it's actually, it was a very great deduction, and it's proved to be exactly the case, that it's the number of times that it's blasting per second, which actually gives the notes. So that then led to a number of people other than myself working on the Beetle. And then I began to take an interest because I could see that this was an example of combustion in nature. And the electron micrographs that Professor Tom Eisner produced actually showed that there was a twin valve system. There was both an inlet valve, which is, this is two combustion chambers, both with their exhaust tubes. I thought that he'd actually cut through sideways here, but he assured me he hadn't. And I then realized that there was a valve, an outlet valve. He had discovered this inlet valve, which is to do with pinching the inlet to stop more fuel and oxidant coming in. And then when I realized that he had not actually sliced through here, but that this was a hard bit of cuticle, we call it, and that there was a membrane, a bit of membrane which was sitting downwards like this. I'll have to show you on this picture that what I was actually looking at was the red line here, which is a bit of membrane which was actually closing an exhaust tube, and that when under pressure that would lift up and that membrane would act like an exhaust valve. So it's really a pressure relief valve. Once I realized that, I then could see that there was something that we could actually copy, and that was the valve system. Just in summary, the Beetle is actually bringing in hydroquinone and hydrogen peroxide. That's the actual chemistry of what's going on. It is bringing those chemicals into this combustion chamber. This is just a schematic here on the right. And those two chemicals are exploding. The very explosion is pinching the inlet valve and closing it off. But the same pressure rise is actually opening the exhaust valve. And that is what one actually sees the Beetle doing, which is really quite extraordinary to see this in operation in such a small system, only 1 millimeter roughly in size for this combustion chamber, which you saw earlier in the electron micrographs. And there's two of them, both going on at once. It's really quite extraordinary. This system of a pressure release valve attached to a combustion system has been used, but people hadn't realized that they were copying the Bombardier Beetle. It was used by the Nazis with the V1 in the Second World War. The Doodlebug was using exactly that principle, and it's called pulse combustion. So an explosion, sounds a bit like a motorbike, and when it ran out of fuel, then the warhead was coming down and did all its damage in London and the home counties. And those Doodlebugs were powered by exactly the same principle. The fuel and the air, it was gasoline, of course, petrol brought in with the air, combusted, burnt, the pressure goes up, it's pushed out of the back, which then propels the V1 a little bit forward, and then the low pressure opens the valve, and the whole cycle is repeated. So that's what the Bombardier Beetle is doing, not to propel itself, although it does have to brace itself when it's firing. You do actually see it bracing itself against being pushed forward, but it's not propelled. It is actually pushed out of the back against a predator. So you're actually got a series, really, of explosions, a gunshot or a machine gun, think of it like that, going out of its backside. That's literally what is going on, but at 500 times or thereabouts per second, which is pretty extraordinary. The chemical system, as I've already indicated, but here is the actual chemistry for those who are chemistry buffs here. We haven't got Nick Cowan here with us, but he would take an interest in this. It's hydroquinone plus hydrogen peroxide, which is not something you play around with. It's very dangerous stuff, particularly pure hydrogen peroxide or high concentration. That which you use in bleach is a very, very weak solution because it's oxidant, and it will oxidize everything that's in your room if you're not careful, including yourself. If you're to have pure hydrogen peroxide, it's hugely dangerous. So, but this is hydroquinone, and it produces benzoquinone, it's the overall reaction here, plus water. And it is catalytically controlled. That is, you've got to have some sort of, you can in a laboratory use a metal catalyst, but what the Beetle does, it uses catalase and peroxidase, which are found in all many living creatures as a natural enzyme, a catalyst to make this work. A very young Richard Dawkins once made quite a thing of this when he gave his lecture to young people way back in the 1990s. But he also made a crucial mistake, and I'm going to highlight what happened. This is his lecture in the Faraday lecture theatre, very sadly now misused by so many evolutionists, including, what's that lady's name? Alice Roberts. Yes, she gave the Faraday lectures one Christmas. She came out with this wonderful statement that we are all apes and, you know, deluding everybody. Michael Faraday would turn in his grave to see his famous science lectures misused like this. But this is Richard Dawkins some years ago talking about the Bombardier Beetle. A certain person from Oxford, and 1991.
In fact, the hydroquinone does nothing at all. We can put that on one side. The true story is that hydrogen peroxide on its own does decompose to form oxygen and water, but it needs a catalyst under normal conditions to do that. This black powder here is a catalyst. It's not the catalyst that the Bombardier Beetle uses. The Bombardier Beetle does use a catalyst, and it does in fact squirt this hot substance into the face of its enemy. But if you put a catalyst into a weak solution of hydrogen peroxide, then you're going to get a little bit of bubbling, and it's a little bit warm. That might have some effect on the predator, that might slightly deter a predator, and it would be not particularly dangerous to the beetle. Now we've got a smooth gradient, a bit more concentration of hydrogen peroxide, and that's distinctly warm. That would work more effectively against a predator. And by moving gradually up the slope, gradually increasing the concentration of hydrogen peroxide, we can end up with... So there is a smooth slope all the way up to the effective deterrent against a predator.
The thing is, he was trying to argue that the hydroquinone was incidental. It's not. It's actually crucial to the system, because the catalysts, which he rightly said are catalase and peroxidase, are not the same as what he was using. When you actually see the real reaction going on in the laboratory using, again, an artificial catalyst, this is what you get.
Yep.
That was a platinum catalyst.
Platinum catalyst.
And now it's your quinone's form. See, that's orange?
Yes, that's the orange. Thank you for showing me this, Garth. This is excellent.
Yeah, that orange there would be your benzoquinone. The bottom orangey color.
So what you can see there is the much stronger reaction that you actually get. And I was talking with Garth Hewitt there at Liberty University. He's moved off from there now, but Garth Hewitt was showing me the huge reaction, which is the crucial one, which Professor Richard Dawkins missed. If you're involved in the chemistry, I won't give you verbally all the detail, but all the detail is on this slide. But I'm just point out the one that he missed. The crucial reaction that he was missing was this one. It is the benzoquinone, which once it gets going, and of course it does need energy going in to get it going. it produces, as you can see, if you see at the top right there, it produces hydrogen. Now, once you've got the hydrogen, then it's the hydrogen reaction with oxygen, which has been liberated from the hydrogen peroxide, which is massively exothermic. That is, produces a huge amount of heat. So to say that that first reaction is unimportant is frankly nonsense. It's very important, because if you don't get that reaction involved, you won't have the hydrogen, and the hydrogen is what makes it such a brilliantly exothermic and makes it go pop in a big way. So the amount of energy you get was much more than what Richard Dawkins was showing. So it's actually a very complicated chemical system. Not only that, the inlet system, it was discovered later, is producing the very chemicals which are going to react in the Bombardier Beetle. The benzoquinone and the hydrogen peroxide are both coming down the same tube. That's not been fully understood. That is a very complicated bit of thermodynamics in its own right, and it's not simple to produce hydrogen peroxide. So what I would just want to draw to your attention is that what we copied is that we mimicked the valve system. And what I'll just show you here is a little clip from a computer visualization of what we eventually did in the laboratory. What we did is that we proposed that really what's going on is it's a bit like a pressure cooker. You're producing steam, because much of what is being heated is water. You've only got a hydrogen peroxide and hydroquinone for a small part of the mixture, which is itself doing the heating that I've just described. We didn't copy the chemistry. We actually built a system, of which this is a computer model of what we finally built, which was essentially electrically heating water. In the Beetle, it's chemically heating what is mainly water, which is producing steam. So we decided that we would just do a computer visualization to make sure that we'd understood what was really necessary for us to grasp for copying in the laboratory. So you don't need to worry about all the detail here, but we estimated what the chamber, of which this is 1/8 of it, so it's actually a cylinder, and we basically said that this is all full of hot water. It wants to boil. We're going to release a valve at the bottom right, and we're going to let that go and see. We estimated what the volume would have to be. So we said it was about 0.2 of a millimeter, 0.3 millimeters in radius. And we just let the membrane go. We had made some assumptions about the fluid dynamics, which I won't go into here. And then we let this go. And the motion of the liquid is coming out because it wants to boil. As soon as the pressure is released with this membrane here, then it changes to a gas, which of course is steam in this case. And the clock going at the top right is telling us how much time has gone by. And when it's basically all exhausted and it's mainly brown and red, that means that it's mainly steam which has come out and most of the water has been ejected. And we found that that happened. As you can see, the clock is reading at approximately 3 milliseconds. We knew that that would be consistent with about 300 cycles per second. So we knew we were in the right ballpark. And we grasped then that what really was going on was heating essentially what was water. We're going to heat it electrically. So we decided to build a system very similar to that, but a little bit much bigger, to be frank, not just a little bit, a lot bigger than the Bombardier Beetle. So we built an experimental rig, and this is the first one actually working, with a very sophisticated receptacle on the right for receiving the steam. And this was a laser in order to measure the size of the droplets. And we were very pleased to get this right. And we could see that the principle we had definitely established by our rig, which was about 20 times the size of the Bombardier Beetle's combustion chamber. So we scaled this up, that is, we got it going much faster, and at the work has actually been used for an application to diesel fuel injectors. It actually is being used in Sweden for a diesel fuel injector. What we're considering doing is using it for fire extinguishers, which I'll come to in a moment. This is another example of the model, and this shows it going much, much faster. So we developed it further with a company called Swedish Biomimetics 3000, which actually funded much of the later work that we did at Leeds. What we are aiming to do is to possibly apply this for fighting fires, and I'll just show you a little bit of this as we close. The application, as I mentioned, is to fuel injectors, aerosols, nebulizers. We have had people interested in that, but let me just say a little bit about fire extinguishers as we close. There's a lot of dangerous wildfires that have taken place in America, in Australia, in even in parts of Europe, as well as terrible floods, the opposite problem. But there's been a number of wildfires in recent years, and what it's reckoned is that the fire extinguisher which adopts this principle, can actually be used to shoot water and steam a considerable distance. From a 2-centimetre chamber, which we were using, we could actually get the system throwing water and steam a distance of about 4 meters, which could protect a firefighter. So this was a small chamber in comparison with what would be used for a real fire extinguisher, but we are in the process of developing this in America, and with a view to getting the fire extinguisher industry interested in that. So I'm just to say one last point, and that is some years ago, Professor Richard Dawkins criticised myself and Stuart Burgess as ones who really didn't understand the science. You know that Professor Stuart Burgess has raced ahead with his wonderful work on the Olympic bikes. My little claim to fame is that I was given a particular award in 2010 for outstanding contribution to innovation and technology with the University of Leeds and with my sponsor, Swedish Biomimetics 3000. So the work was honoured, if you like, not to my glory, but to the glory of God, who made the Bombardier Beetle, and the inspiration that I perhaps drew from it. And I think the last word was not to Professor Dawkins, but the last word is always to God himself. And so both Stuart and I, in the work in biomimetics, he's done a lot more than I have, but in all our work, we're seeking to give glory to God. So thank you very much.